Tonight, we're going to revisit a cosmic disaster story you've probably heard your whole life. The one where the Andromeda galaxy is racing toward the Milky Way like a celestial wrecking ball, set to smash our home galaxy to pieces in about 4 billion years. Documentaries frame it as an unavoidable doomsday. Headlines call it a galactic collision course. The message is simple. The Milky Way is doomed. That story feels clean, direct, a straight line from now to annihilation. For years, Hubble's measurements seem to back it up, tracking Andromeda's motion across the sky and turning tiny shifts in starlight into a prediction. A nearly head-on crash that would rip both galaxies apart. Scientists ran simulations showing spiral arms shredded into tidal tails, stars flung into intergalactic space, and a new, monstrous Milkdromeda rising from the wreckage. It sounded like the ultimate apocalypse in space. But reality, as James Webb is now revealing, is quieter and far stranger. Webb's infrared vision is cutting through Andromeda's dust, resolving the crowded core, the extended halo, and even the faint streams of stars that surround the galaxy. Those details are forcing astronomers to admit something uncomfortable. The old collision story was, at best, incomplete. At worst, it was fundamentally wrong about what destruction really means on the scale of galaxies. Before we get started, it's worth shrinking this drama down to a human scale. This isn't only about a far future spectacle no one alive today will see, it's a test of whether the models used to predict the future of the entire cosmic web can be trusted. If the nearest giant neighbour in our own local system doesn't move the way every spacecraft, telescope and theory said it should, what does that say about how galaxies live, die, and merge far beyond our corner of space? Here's the central contradiction. Hubble painted Andromeda as a cosmic battering ram aimed straight at us. The sideways or tangential motion looked tiny compared with the speed at which it was falling inward, so simulations locked in a direct hit. But Webb, combined with other precision missions, is now hinting at something no one expects. A subtler sideways drift, a more complex mass distribution and an interaction that looks less like a head-on crash and more like a slow, orbital dance around a shared centre of mass. No one predicts a gentle waltz when the word collision is used. Yet that's exactly the picture beginning to form. Stars in both galaxies are so far apart that even in a merger, almost none will physically collide. Gravitational tides will reshape orbits, not vaporize planets. The solar system won't be shredded, it will be relocated. By the end of tonight, you're going to understand how Andromeda will really change our night sky, what happens to the Sun as the galaxies entwine, and why absolutely no one anticipates the calm, almost cinematic transformation that the next 10 billion years now appear to hold. Now, let's begin. So, how did the story ever become Andromeda will destroy the Milky Way in the first place? To see why Webb's quiet revolution is so dramatic, you have to rewind to a very different space telescope, staring at the same cosmic target. In 2012, scientists used the Hubble Space Telescope to do something incredibly delicate. They watched Andromeda's position on the sky crawl by a fraction of a pixel over several years. From that almost imperceptible drift, they concluded that Andromeda was heading almost straight toward the Milky Way, fast enough that a near head-on collision in about 4 to 5 billion years looked nearly guaranteed. That drift has a name: proper motion. Imagine holding your arm out and tracking a distant aircraft as it moves sideways against the background. The plane might also be flying toward or away from you, but that sideways slide is what Hubble tried to capture for a whole galaxy. Proper motion is that tiny sideways component of motion across the sky, measured over years, and it is absolutely crucial. If the sideways speed is small, the galaxy is a bullet aimed at us. If it is larger, the same galaxy can sweep past, loop around, and turn a crash into a long, spiraling encounter. The original plan was simple. Measure the proper motion, combine it with Andromeda's known approach, speed along our line of sight, and plug both into a gravitational model of the local group. No one expects the math to lie. No one predicts that a barely measurable sideways drift could flip the entire fate of two massive galaxies. But under that confident prediction sat a stack of assumptions. The model depended on how massive Andromeda really is, how heavy the Milky Way is by comparison, and how far their invisible dark matter halos extend beyond the bright disks of stars. It treated those halos as smooth, symmetric cocoons and assumed their mutual gravity would pull the galaxies into a relatively direct smash, not a drawn-out orbital dance with multiple close passes. Tonight, we're going to question each of those assumptions, because Webb has started to probe Andromeda's core and halo in infrared, tracing cooler stars, cold dust, and subtle streams of debris that betray past encounters. From those structures, scientists can back out a more precise mass distribution and a refined motion, revealing that even tiny changes in proper motion can turn destruction into something closer to choreography. And there is a deeper puzzle. What does it even mean to destroy a galaxy when the average distance between stars is so immense that direct stellar collisions are rare? If the solar system is more likely to be gently flung into a new orbit than vaporized, how much doom is left in that headline? Before we get started on Webb's actual measurements, hold that question. Because the next set of numbers does not just tweak the old prediction, it pushes the whole Milky Way Andromeda story right up to the edge of what anyone, absolutely no one, anticipates. What anyone, absolutely no one, anticipates. And if you're still here, several minutes into a deep dive about the fate of the Milky Way, that already says something important. You're not here for a two-sentence scare headline about galaxies smashing in 4 billion years. You want to understand how this system actually evolves, what scientists really discovered, and where the line is between drama and data. That is exactly why this channel exists. Tonight, we're going to follow Andromeda and the Milky Way all the way from first detection of motion to the updated Webb-era timeline. But between those big moments, this channel lives in the details that usually get cut. The sideways velocity numbers that change the entire collision story. The dark matter halo models that quietly shift whether this is a slam, a slide, or an orbital dance. The quiet, precise measurements that never make the headline, but completely rewrite the ending. The mission here is simple to say and hard to do. Take the space stories that get misreported into apocalypse trailers and rebuild them from the ground up so you feel like an insider, not a spectator. When scientists argue over how fast a galaxy is moving or where the true boundary of a halo lies, you see why it matters, how the data is taken, and what it means for planets, for stars, and for the long-term future of the solar system. Pattern interrupt for a second. While this video runs, some of the most advanced spacecraft and telescopes ever built are quietly pulling in photons from Andromeda's core, its halo, and the thin streams of stars that trace past encounters. Webb in the infrared, Hubble in the optical, Gaia mapping motions, radio arrays, listening to hydrogen and cosmic wind. All of that effort is aimed at the same question you're asking. What actually happens when two giant galaxies meet? If that's the kind of question that keeps you watching, take a moment right now to tap like or subscribe while you're already here. It's a tiny action, but it genuinely pushes these long-form explorations out to more people who care about science and space as much as you do. No one expects a single click to matter against billions of stars, but for this mission it changes what can be researched, animated, and explained next. Because this episode is only one chapter. Coming up are full breakdowns of how galaxy mergers trigger starburst regions, how dark matter halos decide whether galaxies collide or just orbit, and how the last generations of stars will burn in the merged Milkdromeda system. By the end of tonight, you're going to understand why the word destroy never told the real story. Now that we're on the same team, let's rewind to the moment astronomers first realized Andromeda was even moving toward us at all. Astronomers did not always know a giant spiral was bearing down on the Milky Way. For a long time, Andromeda was just a fuzzy nebula in early telescopes, a smudge of light that seemed safely tucked inside our own system of stars. Then, in the early 20th century, that quiet assumption shattered. Before we get started, imagine the moment when that smudge stopped being local. When Edwin Hubble measured Cepheid variable stars in Andromeda in the 1920s, he discovered they were far too bright and far too distant to belong to the Milky Way. Overnight, Andromeda transformed from a cloud in our backyard into an island universe in its own right, a separate spiral galaxy, roughly comparable in mass and in many ways even bigger in diameter than our own. Expectation, a harmless patch of gas. Reality, another great star city bearing down on us across intergalactic space. Once Andromeda was recognized as a full galaxy, the next question was unavoidable. How is it moving? Tonight, we're going to step into those early observatories where scientists turned from simple images to spectra, spreading out Andromeda's light into rainbows crossed by dark absorption lines. Those lines were not where laboratory measurements said they should be. They were shifted. That shift was the Doppler effect, written in starlight. By measuring how far those spectral lines were displaced toward the blue, astronomers could calculate Andromeda's radial velocity, the component of its motion directly along our line of sight. The answer was unsettling, about 110 kilometres per second, toward us, not drifting away with the general expansion of space, but cutting inward against the cosmic wind. Radial velocity is only half the story, though. It tells you whether an object is approaching or receding, not whether it will actually hit. The missing piece is proper motion, the tiny sideways drift across the sky, measured in fractions of an arc-second per century. For decades, Andromeda's proper motion was far too small to detect. Scientists knew the galaxy was getting closer. They did not know if its trajectory was a direct bullseye or a near miss. So the 20th century view was filled with tension. On one hand, the Milky Way and Andromeda were recognized as the two dominant members of a gravitationally bound local group, surrounded by dozens of smaller galaxies all orbiting a common center of mass. On the other hand, the exact choreography of that bound system remained hidden, like watching planets from across the solar system with your hand over half the data. Was Andromeda on a collision course destined to merge with the Milky Way in a spectacular galactic crash, or were the two spirals locked in a slow orbital waltz that would only graze their outer halos? No one expects a neighbour galaxy to be both so close in cosmic terms and so uncertain in its path. No one predicts that absolutely no one anticipates the true complexity of their future encounter. By the end of tonight, you're going to understand how that uncertainty drove generations of missions and measurements, and how later telescopes would finally reach for Andromeda's sideways motion and change the story from inevitable destruction to something far stranger. So when Hubble finally stepped into this story, the stakes were already enormous. For decades, scientists knew Andromeda was racing toward the Milky Way in space, but the sideways part of its motion, the one detail that decides collision or near miss, remained hidden in the noise. Here's the challenge. Andromeda sits 2.5 million light-years away. At that distance, its sideways drift on the sky is measured in fractions of a milliarc second per year. That's an angle so small you could watch a coin on the moon move a few centimetres over a decade and still be trying to squint hard enough to see it. No one expects that kind of motion to be easy to pin down. Tonight, we're going to stand next to Hubble as it attempts something almost absurd, turning that invisible drift into a hard number. The strategy is elegant. Use Hubble's razor-sharp vision to stare at bright stars and compact clusters embedded in Andromeda's disk. Wait years. Come back. Then, with the same spacecraft, the same cameras and the same reference grid of distant background galaxies, measure how those targets have shifted by mere pixels. This is not a single snapshot. It is a long baseline experiment stretched across multiple observing campaigns. Astronomers stack images, correct for distortions in Hubble's optics, track the subtle breathing of the telescope as it orbits Earth, and average over thousands of stars to tease out a proper motion signal from the jitter of noise. Milliarc seconds become data points. Data points become a velocity vector. In 2012, that work finally crystallized. The sideways motion Hubble measured for Andromeda was small, surprisingly small, compared to its headlong approach speed of about 110 kilometres per second. Expectation, perhaps a wide grazing pass, a cosmic flyby where both galaxies shear past and drift apart. Reality. The velocity vector pointed almost straight at the Milky Way. The solar system was no longer just in a shared neighbourhood, it was on a nearly direct line with a galactic battering ram. Now, let's begin to see what that means. Feed Hubble's numbers, Andromeda's approach speed, its tiny sideways drift, and best estimates of both galaxies' masses into N-body simulations. Let gravity do the rest. The computers show the same drama, again and again. First encounter in about 4 billion years, a near head-on plunge. Tidal tails of stars flung out like glowing ribbons, gas clouds shocked and compressed into furious starburst regions. By around 7 to 8 billion years from now, the Milky Way and Andromeda are no longer distinct. They've merged into a single, swollen elliptical system that some scientists nickname Milkdromeda. This is not a wild late-night guess. The 2012 Hubble study was deeply peer-reviewed, led by experts who understood every quirk of the spacecraft and every boundary of the data. That authority mattered. Textbooks rewrote their chapters. Planetarium shows projected colliding spiral galaxies across domed ceilings. Documentaries, popular science books and headlines all repeated the same confident line. Andromeda will collide with the Milky Way. By the end of tonight, you're going to understand why that story held so firmly for a decade, and why absolutely no one anticipates what happens when Gaia, and then Webb, start to tug at the edges of Hubble's perfect-looking prediction. Now, let's begin. When most people hear galaxy collision, the mental image is simple: two solid island universes slamming together like cars on a highway, stars smashing, planets shredded, the Milky Way obliterated in a single apocalyptic impact. That picture feels intuitive, because in everyday life, Collisions are violent, fast, and final. But space does not play by everyday rules. Before we get started on Webb overturning predictions, it helps to rewrite that image in your head. A galaxy is not a solid object. It is a vast, gravitationally bound system of stars, planets, gas, dust, and dark matter, with almost all of its volume as empty space. The typical distance between neighbouring stars in a galactic disk is measured in light years. Put two such systems on a collision course, and something strange happens. Almost nothing actually hits. Run the numbers, and the chance of any two sun-like stars physically colliding during even a direct merger is vanishingly small. Trillions of kilometres of emptiness separate them. So, when astronomers say Andromeda will ram into the Milky Way, they are not picturing a solid crash. They are picturing a slow, graceful, and incredibly complex gravitational ballet that unfolds over billions of years. Here is what really happens. As the galaxies fall toward each other, their mutual gravity reaches out first. Tidal forces grab the outer disks and begin to stretch them, pulling out long, delicate streams of stars and gas. Spiral arms twist and shear. Great arcs of material are flung tens of thousands of light years into intergalactic space, forming tidal tails that wrap around the merging pair like thrown ribbons. Where gas clouds from each galaxy pass through the same regions, the story changes again. The gas feels pressure, is compressed, and collapses. The result is a starburst. Huge knots of new stars ignite in the overlapping zones, lighting up like cosmic fireworks. No one expects a quiet sky here. Ultraviolet light from newborn clusters pours out, while supernovae and stellar winds carve bubbles in the glowing debris. Over time, orbital energy is shuffled around. Ordered, flat spiral disks become tangled and puffed up. Stars are scattered onto new, more random paths. The two elegant spirals that began the mission end as a single, larger, more spheroidal remnant, something like the giant elliptical galaxies seen at the centres of clusters. The Milky Way is not destroyed, it is remodeled. So, destroy is a misnomer. The galaxies do not explode, they do not vanish, they merge. Shapes are warped, orbits are traded, the internal architecture of each system is rearranged by gravity. But most individual stars, and the planets bound to them, simply keep orbiting along new trajectories, largely unscathed, now residents of a different-looking home. Here's the pattern interrupt. If even a direct, head-on merger leaves almost every star intact, what exactly were scientists warning about when they talked about Andromeda tearing the Milky Way apart? Tonight, we're going to push on that question. Because once Gaia and then Webb started to pin down Andromeda's true motion through space, the whole idea of a simple, catastrophic crash began to unravel, and a quieter, stranger fate emerged at the boundary between prediction and observation. So if the old headline, Andromeda will destroy the Milky Way, is cracking, what takes its place? Before we get started on the new picture, it helps to lay out the old one, because the popular story you've heard for years rests on at least 7 big myths repeated so often they feel like facts. Myth 1. That Andromeda is flying straight at us in a perfectly head-on trajectory, a cosmic battering ram aimed precisely at the Milky Way's heart. In that version, there's almost no sideways motion, no graceful orbit, just a direct plunge through the centre of our galaxy. Myth 2. That the Milky Way will be destroyed in this encounter, as if one clean impact will rip the spiral arms off, erase the disk, and leave only a chaotic smear of stars where a structured galaxy used to be. The word suggests a single moment of impact, a galactic car crash, Myth 3. That the Sun and everything in the solar system is almost guaranteed to die in the chaos, either flung into deep space, swallowed by a black hole, or roasted by some cataclysmic wave of radiation when the galaxies finally merge. In that telling, our star is living on borrowed time. Myth 4. That when galaxies collide, stars themselves smash together like billiard balls, turning the sky into a shooting gallery of direct impacts. It's a mental image that's hard to shake. Suns physically hitting suns, planets vaporized in an instant. Myth 5. That the timeline is fixed and precise, with a first collision in about 4 billion years, a second pass in 5 or 6, and a final, settled Milkdromeda not long after. In this script, every close pass is scheduled, every orbit locked in, as if the whole mission has been pre-programmed. Myth 6. That astronomers already know the exact masses of both galaxies from the central black holes to the faint outer halos, so the merger can be simulated like a solved problem. The Milky Way and Andromeda are treated as tidy, well-weighed systems. And myth 7, that dark matter is just a quiet background player, a passive halo that barely affects the drama, while the visible stars and gas do all the interesting work. In that view, the real action is in the bright disks, not in the invisible boundary beyond. Now, let's begin to pull these apart. Many of these aren't outright lies, they're exaggerations or older simplifications built on pre-Webb images, early Hubble proper motion measurements and simulations that had to guess at key numbers. Expectation? A clean, direct hit. Reality? Gaia and Webb are revealing a messier orbital dance. Tonight, we're going to use those new measurements, star motions, cold dust maps, warped disks, to revisit each myth. By the end of tonight, you're going to understand which fears were misplaced, which warnings were dead on, and which ideas transformed into something far stranger than a simple doom story. So keep score as we go. Head-on impact, total destruction, solar system doom, star crashes, fixed timeline, known masses, quiet, dark matter. Which ones survive contact with Webb's data? To keep score, you need to know who's actually playing. Not just names in a textbook, but the real structures, the hidden mass, the invisible battlefield where this mission will unfold. Before we get started on orbits and timelines, meet the two giants sharing space with you right now. The Milky Way is not a flat pinwheel, it's a barred spiral galaxy, a layered system of components all locked together by gravity. At the centre sits a dense bulge of old stars and a supermassive black hole wrapped by a bright bar of stars that channels gas inward like a conveyor belt. Around that, a thin rotating disk hosts the familiar spiral arms, where gas, dust, and newborn stars trace glowing lanes across tens of thousands of light years. Outside, that postcard image is more. Above and below the thin disk lies a thicker, puffier disk of older stars, moving on more tilted, chaotic paths. Beyond that, a faint stellar halo extends in all directions, sprinkled with ancient star clusters and the shredded remains of smaller galaxies the Milky Way has already consumed. Designed on paper, it looks neat and orderly. In reality, it's a fossil record of past collisions written across the sky. But even that isn't the full system. All of those visible stars and planets are swimming in something far larger, a dark matter halo. Think of it as an invisible, nearly spherical cocoon that does not emit light, does not reflect it, but dominates the mass. The solar neighbourhood, the spiral arms, the central bulge, everything orbits inside this halo, like dust motes drifting in a vast, transparent globe. Andromeda, M31, is the Milky Way's heavyweight rival. Slightly larger in stellar extent and likely more massive overall, it hosts its own bright disk, central bulge, and sprawling halo. It's ringed by a swarm of satellite galaxies, just as the Milky Way is trailed by the Magellanic clouds and dozens of dwarfs. Two island universes, each with its own retinue, sharing the same cosmic neighbourhood and moving through the same intergalactic medium. Tonight, we're going to treat those bright disks as the visible tips of much deeper systems. In simple terms, Andromeda's dark matter halo is at least as big as the Milky Way's, maybe bigger. If the Milky Way's visible disk were the size of a dinner plate on your table, its dark matter halo would be a sphere the size of a house around it, and Andromeda's house is right next door. Stretch that comparison into space, and something unintuitive appears. The starlight says the galaxies are still millions of light-years apart. The halos say their outer regions may already be touching. No one expects a galactic collision to begin long before the pretty spiral arms overlap. But gravity doesn't care about what human eyes can see. So, when scientists say collision, they're really talking about the slow interpenetration of these enormous dark halos first, setting the boundary conditions for everything that follows. The bright disks and their planets are passengers. The dark matter is the driver. And as Webb starts weighing those halos with unprecedented precision, absolutely no one anticipates what it implies about whether Andromeda is charging straight at us or quietly sliding into a much stranger orbital dance. To know whether Andromeda is going to smash into the Milky Way or just brush past, you need one thing above all else: weight. Not of a single star, of an entire galaxy. Tonight, we're going to weigh something so large you can't even see all of it, using tools that never touch a single atom. Now, let's begin. The first trick is the galaxy rotation curve. Scientists measure how fast stars and gas orbit at different distances from the centre, the way you'd clock the speed of cars on a circular racetrack. Near the core, you expect high speeds. Far out in the disk, gravity should weaken, so the orbital speeds should drop, just like planets in our solar system. That's the prediction. Reality refuses to cooperate. In both the Milky Way and Andromeda, the rotation curves stay flat. Stars tens of thousands of light-years out orbit almost as fast as stars much closer in. The only way to hold those fast movers in bound orbits is with extra mass, a lot of it. Dark matter halos so massive they outweigh the visible stars and gas by factors of 5 to 10. By the end of tonight, you're going to understand why tiny changes in those speeds ripple all the way out to the fate of both galaxies. But here's the problem. There is no single number for the mass of Andromeda or the mass of the Milky Way. Depending on which tracer you use, you get different answers. Track stars in the inner disk, you sample one region, use cold hydrogen gas, you probe farther out. Follow globular clusters and satellite galaxies, you push deep into the dark halo. Each method has its own uncertainties. Change the assumed distance, change how far out you trust the curve. The total mass swings by a factor of 2 or more. Pattern interrupt. That factor of 2 uncertainty isn't just an academic argument. It decides whether the Milky Way-Andromeda system is gently bound in a wide orbit or locked on a tightening spiral that ends in a full merger. This is where Gaia changes the game. The Gaia mission measures positions and motions of more than 1 billion stars in our own system, with exquisite precision. Proper motions, radial velocities, tiny accelerations in the solar neighbourhood. From that, scientists reconstruct the Milky Way's mass distribution. How much sits in the bulge, the disk, the halo. Gaia also tracks some satellite galaxies, revealing whether they're just passing through or tightly bound, which in turn anchors the outer dark matter profile. The heavier the halos, the stronger the mutual pull. Boost the total mass, and the orbit shrinks. Lower it, and you move closer to a distant flyby. No one expects a small tweak in mass to rewrite the long-term orbital dance, but that's exactly what happens. And while Gaia maps our backyard, Webb stares outward. Its infrared eyes cut through the dust in Andromeda's core and disk, resolving crowded star fields, cold gas, and dust lanes. Webb refines Andromeda's rotation curve in the inner regions, measures star-forming rings, and constrains how mass is packed into its bulge and bar. Combine that with Gaia's Milky Way map, and suddenly the initial conditions for Andromeda's approach are sharper than ever. Absolutely no one anticipates how much that clarity will change the prediction of what happens when these two giants finally meet. That clarity doesn't come from nowhere. It comes from a new kind of eye in space. Tonight, we're going to watch the James Webb Space Telescope turn Andromeda from a fuzzy threat on the horizon into a precisely mapped neighbouring system with a very different future. Before we get started, place Webb in your mental star chart. It's parked at the second Sun-Earth Lagrange point L2, about 1.5 million kilometres beyond Earth, where the gravity of the Sun and our planet balance the spacecraft's orbit. Out there, a 5-layer sunshield keeps it colder than 50 Kelvin. Cold enough that its 6.5-metre segmented mirror can drink in faint infrared light without being drowned by its own heat. That infrared vision is the key. Visible light bounces off dust and gets blocked in crowded galactic centres. Infrared slips through. Webb sees the glow of cooler stars, warm dust, and molecular gas that Hubble and ground-based telescopes only hinted at. Where older images of Andromeda's core look like a bright, overexposed glare, Webb resolves structure. Lanes of dust, nested rings, and the dense swarm of stars orbiting a central black hole. Now, let's begin with what scientists actually pointed this observatory at. Recent Webb programs have zeroed in on Andromeda's central bulge with razor-sharp imaging, tracing how stars crowd toward the middle and how dust spirals inward. Other campaigns map star-forming regions along its spiral arms, catching the red glow of hydrogen clouds and the warm dust cocoons where new stars ignite. Spectrographs on Webb split that infrared light into fingerprints, revealing the chemistry and motion of dust and gas as they stream through the galaxy. Those spectra turn pretty pictures into hard numbers. Tiny shifts in wavelength show how gas flows along the spiral arms, how fast material orbits in the bar, and where shocks compress the interstellar medium. Webb doesn't just see where Andromeda is bright, it measures how its internal wind of gas and dust moves, twists, and collides. By the end of tonight, you're going to understand why that matters so much. Because when Webb resolves individual stars in Andromeda's disk and halo, it lets scientists sort them by age, metal content, and distance. Old red giants in the halo, younger blue stars in the arms, intermediate populations in the bulge. Each group becomes a tracer of mass. Refined distance ladders tighten how far away those stars really are. The result is a sharper map of how mass is distributed across the entire galaxy. No one predicts Webb will replace Hubble's direct measurements of Andromeda's sideways drift across the sky. It can't. But it does something just as disruptive. It feeds dynamical models with far better inputs, a more accurate rotation curve, a clearer view of the bar and bulge, and a detailed star formation history written in infrared. Simulations of the future orbit no longer rely on a rough sketch of Andromeda's interior. They use a high-resolution blueprint. Combine that blueprint with Gaia's exquisite map of our own Milky Way, plus updated proper motion studies, and the old picture of a simple head-on crash starts to wobble. The boundary between collision and orbital dance shifts. In the next section, those merged datasets will redraw the script for our galactic future, and absolutely no one anticipates how different it looks. The wobble in that picture doesn't stay small for long. When scientists went back to Hubble's 2012 measurements armed with better models and fresh data, the story of a direct hit began to bend, not into safety, but into something subtler and stranger. The original plan is simple. Measure Andromeda's proper motion with Hubble, combine that with its line-of-sight speed, and project a nearly straight plunge toward the Milky Way's centre. No one expects much sideways motion. The early analysis put Andromeda's tangential velocity at only a few tens of kilometres per second. Almost a cosmic battering ram aimed right at our solar system's broader neighbourhood. Then the rechecks begin. Teams reanalyze Hubble's images with improved distortion corrections. They fold in Gaia's exquisite map of local group stars and satellites, using the motions of smaller galaxies as test particles in the shared gravitational field. They try alternative dynamical models for the whole system. Each iteration nudges Andromeda's sideways speed upward, still tens of kilometres per second, not hundreds, but enough to matter. Here's why that tiny change is huge. In space, over millions of light years and billions of years, a lateral velocity of 30 or 50 kilometres per second doesn't stay a small correction. It compounds into a radically different track. Instead of a nearly head-on plunge, the orbit shifts toward an off-axis encounter where both galaxies loop around a common centre of mass before truly interpenetrating. Think less car crash, more slow-motion flyby that tightens into a spiral. Now, let's begin to add Webb. JWST isn't just taking pretty infrared portraits of Andromeda, it is resolving the structure of its bulge, disk, and halo, tracing cold dust lanes, star-forming regions, and the motions of different stellar populations. Those observations sharpen estimates of Andromeda's total mass and, crucially, how that mass is distributed between its bright disk and its dark matter halo. Change the mass distribution and the gravitational tug-of-war changes. The Milky Way and Andromeda do not simply fall into each other. They orbit their shared centre, exchanging energy and angular momentum. By the end of tonight, you're going to understand that Webb's refined mass models feed directly into new simulations, which now favour scenarios where the first encounter is a long, wide pass, not an immediate, deep overlap of the disks. That doesn't mean no merger. The galaxies still converge, but the path looks more like an orbital dance with one or more sweeping passes, tidal tails unfurling, and only later a slow coalescence into a single remnant. The drama spreads out over billions of years, the exact timing and geometry less certain than the old headlines claimed. No one predicts the precise choreography yet. And here's the key reversal. The iconic story of a single catastrophic impact is giving way to a narrative of complex gravitational choreography, tuned by tiny sideways motions and subtle mass maps. Before we get started on those full-scale simulations, there is one more twist hidden in Webb's view of Andromeda's outskirts, a twist that may shift the script yet again. That one shot and its over-image of Andromeda slamming into the Milky Way comes from a very specific place in time. In 2012, Hubble finally measured Andromeda's sideways motion across space, and the numbers looked terrifyingly clean. Almost no lateral drift, a nearly straight plunge along the line connecting the two galactic centers. To visualize it, scientists ran simulations where our spiral disk and Andromeda's disk lined up like two targets on the same bullseye. In those classic animations, you watch Andromeda grow in the sky, fill it, and then, in a single catastrophic pass, the two bright cores rush together. Disks overlap centrally, spiral arms dissolve. Within a few 100 million years, the graceful spirals are gone, replaced by one swollen, amorphous, remnant galaxy. From that perspective, the mission profile for our entire solar system looks simple. Endure one apocalyptic impact event, then adapt to whatever is left. But that was expectation. Reality is already drifting away from it. With Gaia's star-by-star motions, deeper mass maps, and Webb's infrared view of Andromeda's dust lanes and hidden stellar populations, the velocity vector has been sharpened. It is not a perfect bullseye. Andromeda appears to be coming in on a slightly offset trajectory, with just enough sideways motion that the two galaxies miss a direct, central, core-on-core hit. Now, let's begin to reframe the encounter. In updated simulations that use these refined velocities and mass estimates, Andromeda does not simply spear through the Milky Way. It sweeps past. The first pass is a close encounter, not a dead-center crash, and the centers of mass slide by each other before gravity hauls them back for another round. No one predicts a neat, single smash anymore. The path looks more like a looping, tangled dance. Here is the pattern interrupt. An off-axis collision can be even more dramatic for spiral structure. In those runs, tidal forces grab the outer disks and twist them. Long, thin stellar streams are pulled out like ribbons, arcing tens of thousands of light years into intergalactic space. Spiral arms stretch, warp, and reconnect. Both galaxies get flung onto elongated orbits, overshooting, slowing, then curving back in like two spacecraft performing repeated gravity assists around each other. For the solar system, that means the word destroyed is misleading. By the end of tonight, you're going to understand that this is not a single impact event. It is a sequence, multiple passes. Each flyby reshapes the galaxies a bit more, then they drift apart for hundreds of millions of quiet years. The night sky becomes strange but stable. Colossal tidal tails, new arcs of star formation, Andromeda's core sliding across the heavens instead of detonating it. Myth number one, the perfect head-on smash, is almost certainly false. The future is messier, slower, and far more visually spectacular than those early Hubble-era animations suggested. And the next twist comes when scientists ask a harder question. In this drawn-out orbital dance, where does our own star actually end up? In popular imagination, that question has a brutal answer. Say, Andromeda will destroy the Milky Way, and the mind jumps to a single image. A cosmic train wreck where galaxies shatter, stars explode, planets vaporize, and our entire system disappears in a flash of violence. It sounds like a cinematic ending. It is not what the physics actually predicts. Tonight, we're going to peel that word apart. Destroyed. Because in galactic dynamics, destruction looks nothing like a nuclear blast. It looks slow, it looks graceful, and it leaves far more behind than it erases. In high-resolution simulations of major mergers, the first thing to go is not the stars, it is the order. Those thin, rotating disks that define the Milky Way and Andromeda begin to warp, twist, and sprout tidal tails, vast streams of stars and gas flung tens of thousands of light-years into intergalactic space. Spiral arms blur, rings shear. Over a few billion years, the clean spiral patterns are disrupted and then erased. But the stars themselves, they do not vanish, they are resorted. Instead of a flat, rotating disk, gravity sculpts a new, larger, more spheroidal galaxy, a swollen, football-shaped remnant astronomers sometimes nickname Milkdromeda. The orbits of individual stars are scrambled into a puffier halo and a thickened central body. The Sun, if it is still shining, is far more likely to be gently migrated to a new, wider orbit than slammed into another star. No one predicts a chain reaction of stellar collisions because the average distance between stars is so vast that even colliding galaxies barely let them touch. So is the Milky Way gone at that point? Structurally, yes. As a neat spiral disk galaxy, its identity ends, but dynamically and chemically, it lingers. By the end of tonight, you're going to understand that astronomers can still tell where those stars came from. They carry chemical fingerprints, slightly different mixtures of heavy elements like iron, magnesium, and oxygen that reflect each galaxy's star formation history. They carry orbital signatures. Some groups of stars loop in elongated paths, others in more circular or tilted tracks, betraying which original system they belong to before the merger. In that sense, the Milky Way is not destroyed. It is transformed. Its orderly disk dissolves, but its stars, clusters, and many planetary systems survive, now embedded in new orbits inside the merged remnant. Planets may feel a changing gravitational landscape, a shifting night sky, a different galactic wind of radiation and interstellar gas, but not instant annihilation. And this is where Webb changes the story. Before we get started on pure theory, Webb lets scientists look at real mergers in the distant universe in infrared, where dust-shrouded cores and hidden starburst regions are exposed. The spacecraft is catching galaxies mid-collision and long after the fact, revealing faded tidal tails, mixed stellar populations and swollen spheroidal remnants. No one expects these distant systems to match Milkdromeda perfectly, but they anchor the models in observed reality. They show, frame by frame, what after actually looks like, and they hint at a future where our galaxy's end is stranger, subtler, and far more traceable than that single word, destroyed, ever suggested. The next question is obvious. If the Milky Way survives in this transformed state, where exactly does our own solar system end up inside that new galaxy? To answer that, you have to see what happens when other galaxies run this experiment first. Tonight, we're going to walk through Webb's gallery of galactic train wrecks because out there, the future of the Milky Way is already playing out in slow motion. Now, let's begin with a pair like IC 1623, or the famous cosmic cliffs of colliding systems Webb has targeted. In Webb's infrared view, you don't just see two neat spirals politely overlapping. You see disks sliding through each other, dust lanes ripped into corkscrews, and entire regions that look like detonation scars where the gas has been squeezed so hard by tidal forces that it ignites into furious starbursts. To the human eye, in optical light, much of that chaos hides behind dark smears. In the infrared, it glows. This is Webb's specialty. Its filters reach deep into wavelengths where cold, dust and newborn stars live, far beyond what Hubble could routinely see. Those long, reddish filaments in the images are not just pretty decorations. They are the shock lines of gravity, tracing where interstellar clouds have been compressed, shredded, and then reassembled. Embedded inside are stellar nurseries still wrapped in their birth cocoons, completely invisible in ordinary light, but blazing at these longer wavelengths. By the end of tonight, you're going to understand that when galaxies collide, the most important action happens in those obscured regions. That's where the orbits of gas clouds are talked, where the solar systems of the future are seeded, and where the eventual shape of the merged galaxy is written. The bright knots you see sprinkled along warped arms are not random. They are pressure gauges, marking exactly where the gravitational tides are strongest. Look along the edges of these interacting pairs, and another pattern appears. Long tidal tails, sometimes stretching hundreds of thousands of light years, arc away into space like drawn-out commas. Bridges of stars and gas connect one galaxy to another, forming temporary highways across the shared gravitational field. In the centers, Webb often finds twisted bars, off-kilter rings, and dust funnels spiraling toward the heart, where supermassive black holes are likely circling each other, doomed to coalesce. No one expects these systems to look tidy. No one predicts a single clean crash and then silence. Instead, Webb shows a choreography: first approach, first pass, recoil, second pass, long decay. It is messy, extended, and astonishingly common. Across the observable universe, scientists have discovered that galaxies spend a significant fraction of their lives in some stage of this process, and that is the key. The Milky Way and Andromeda are not special targets selected for destruction. They are following a well-trodden path, one Webb is now mapping in exquisite detail across dozens of mergers. When you imagine our future sky, you should picture these Webb images: arms stretched into filaments, star-forming regions, lighting up along tidal bridges, the old spiral patterns slowly unraveling and being rewoven into something new. The real twist comes when you ask, in that slow-motion reweaving, what happens to one small, ordinary solar system trapped inside the flow? The real twist is that even in that chaos, almost nothing actually hits. When most people hear galaxy collision, they picture stars smashing together like billiard balls on a cosmic pool table. Tonight, we're going to dismantle that image because the reality is stranger, emptier, and far more elegant. Before we get started, zoom the scale in your mind. If the Sun were a ping-pong ball sitting in New York City, the nearest star, Proxima Centauri, would be another ping-pong ball all the way in Los Angeles. Between them, not a crowded arcade of balls, but thousands of miles of pure, empty highway. That is what space inside our Milky Way really looks like. Even when two galaxies overlap, their stars pass through each other the way two swarms of mosquitoes pass through the same room. Countless close calls, almost no direct impacts. Simulations make this brutally clear. Take a major merger with hundreds of billions of stars, run it as a detailed n-body calculation, and count the direct star-star collisions. You would expect, with all that mass crossing all that volume, at least a few spectacular crashes. Reality, effectively zero. The number is so tiny compared to the total population that for the purposes of the mission, scientists treat it as none. Orbits twist, disks warp, halos stretch. But stars themselves almost never touch. Pattern interrupt. If stars are missing each other, what is actually colliding in those dramatic Webb images of merging systems? Gas. Unlike stars, gas clouds are extended, messy, and collisional. When two gas-rich galaxies interpenetrate, their cold hydrogen and molecular clouds slam together, shock, and compress. The result is a starburst, a brief, furious episode where the galaxy's normal star formation rate can spike by a factor of 10 or more. Webb sees this directly in infrared knots of newborn clusters buried inside dust, lighting up the tidal bridges and twisted arms as the galaxies fall together. By the end of tonight, you're going to understand that the real danger for a small solar system is not a head-on hit with another star, but the slow violence of changing gravity. As the Milky Way and Andromeda spiral around each other, the combined gravitational field reshapes every orbit. Some stars are flung outward into a vast halo, exiled to the edge of the new Milkdromeda. Others are dragged inward, sinking toward the thickened central bulge. Planetary systems feel this as shifting tidal forces and passing stellar neighbours that come a little closer than they used to. No one predicts that every planet will be shredded, but no one expects every orbit to survive untouched either. Over billions of years, some planetary systems will be destabilized, some outer worlds stripped, some comets redirected, some quiet skies turned into long, slow meteor storms. So myth number 3 of stars smashing everywhere is almost entirely wrong. The real drama is invisible, a gravitational reshuffling of orbits and the fireworks of new starbirth, where colliding gas lights up the dark. Now, let's begin to ask what that means for one particular star and the fragile worlds in its orbit. So when galaxies are gently rearranging instead of violently shattering, the next question hits much closer to home. If an entire spiral like the Milky Way can be stretched and twisted, what chance does one yellow star have? And not just any star, the Sun and the planets clinging to its gravity. Before we get started, it helps to strip away one quiet fear. This is not a scene of planets being flung off like sparks from a grinding wheel. In the most detailed simulations run by teams using Hubble, Gaia, and now Webb-refined inputs, stars like the Sun are not usually hurled into the dark between galaxies. They are not driven straight into the raging core either. The violence is subtler. Orbits are pulled, stretched, and slowly reshaped. Tonight, we're going to follow the Sun through that reshuffling. In model after model, the Sun's path around the galactic centre does not suddenly snap. Instead, the smooth, nearly circular orbit that currently carries the solar system about 26,000 light-years from the Milky Way's core is distorted into a wider, more elongated track around the merged Milkdromeda galaxy. The boundary of home moves outward. The Sun becomes a citizen of a larger, puffier system. The contrast is striking. Expectation, a catastrophic ejection into intergalactic space, the solar system sailing alone beyond any familiar landmark. Reality, a gradual migration to a more distant suburb of the new galaxy, still gravitationally bound but in a quieter neighbourhood, fewer nearby stars, less crowding, more cosmic dark between the points of light. But during the encounter itself, the sky would not feel quiet. By the end of tonight, you're going to understand why simulations describe a spectacle that makes every meteor shower and comet in human history look tame. Over tens of millions of years, Andromeda would swell from a faint smudge into a sprawling, structured rival to the Milky Way's own band, two great spirals overlapping, two sets of planets and star clusters projected across the same dome of space. As tidal forces grow, long streams of stars and gas are pulled out like glowing bridges. Those tidal tails would arc across the heavens, brighter than the Milky Way is today, tracing where gravity has torn and reassembled the galactic disks. Eventually, when the cores of the two galaxies sink together, the night would be dominated by an enormous, dense central glow, the forming heart of Milkdromeda, a single, swollen nucleus blazing across the sky. No one expects this to feel gentle from a visual standpoint. No one predicts a boring sky. Yet for the solar system's internal dynamics, the drama is mostly cosmetic. The Sun keeps its planets. Orbits may be minutely perturbed by distant flybys, but the dominant gravity remains the Sun's own. There is, however, a different clock running. By the time this slow collision is well underway, the Sun will be more than 7 billion years older, its nuclear core more exhausted, its outer layers expanding into a red giant, flooding the inner solar system with heat. For Earth, that stellar evolution is a far more immediate threat than any galactic wind or passing star. So the paradox is stark. The galaxy can collide and merge around the solar system, sculpting a new Milkdromeda in the sky, while the real danger comes from within. A sun that is quietly aging toward a phase that may strip Earth of oceans, atmosphere, and perhaps habitability, long before the last tidal tails fade. And that raises one final question. If the Sun's future is already sealed, what about the black holes at the centers of both galaxies, now destined to meet? So, if the black holes are not the real executioners, what is? To answer that, the timeline has to be laid out with brutal clarity. Tonight, we're going to put Andromeda and the Sun on the same cosmic calendar and see which one actually runs out the clock on life as we know it. Now, let's begin. The revised Andromeda Milky Way encounter starts gently. In about 4 billion years, the first close approach begins. Not a single impact, but a long gravitational handshake. Over the next 1 to 2 billion years, the two spiral galaxies loop, stretch, and twist, throwing out tidal tails while their disks interpenetrate. By around 7 to 8 billion years from now, simulations show a relaxed merger remnant. An enormous, smooth Milkdromeda, the original spiral patterns erased. That sounds apocalyptic, until the Sun steps onto the stage. Stellar evolution models say the Sun is already brightening, very slowly but relentlessly as hydrogen fuses in its core. In just 1 to 2 billion years, long before Andromeda swells dramatically in the sky, the increased solar output is expected to drive Earth into a runaway greenhouse. Oceans evaporate. Water vapor, a powerful greenhouse gas, traps more heat. The climate spirals away from habitability while the galaxy merger is still only a distant rearrangement of star fields. This is the contrast that almost no one expects. The iconic collision, the one that fills animations with crashing planets, is scheduled to peak billions of years after the real crisis for Earth's biosphere. By the time Andromeda's stars begin to truly intermingle with those of the Milky Way, Earth, if it still exists, is likely to be a desiccated, sterilized world, hugging a star that has simply become too luminous. Push the clock further. Around 5 to 7 billion years from now, the Sun exhausts its core hydrogen, swells, and transforms into a red giant. Its outer layers expand outward, maybe past Earth's current orbit, maybe just short of it. But in either case, the inner solar system is drowned in intense radiation and stellar wind. Any remaining atmosphere on Earth is stripped. The crust can be partially vaporized. Surface environments are not merely uncomfortable, they are erased. So an advanced civilization with roots on Earth faces a clear requirement. Long before Andromeda's gravity has fully reshaped the system, it has to solve the moving worlds problem. Migrating habitats to outer orbits, building artificial worlds in the Kuiper belt, or hopping to other stars entirely. By the end of tonight, you're going to understand that this is not optional engineering, it is mandated by stellar physics. Myth number 4 has it backwards. Andromeda is not the primary killer. The sun is the real ticking clock, and the merger is the spectacular backdrop playing out while that clock winds down. But if the sun is the main threat, what happens when two central black holes, each millions of solar masses, are thrown into that same drama? So pause the equations, forget velocity vectors and black hole dynamics for a moment. Tonight, we're going to stand on a future world and just look up. Picture a planet that shares Earth's distant fate. The sun has migrated outward through the Milky Way's disk, dragging this entire solar system along like a tiny raft in a slow galactic river. Generations rise and fall, continents shift. The mission of civilization itself changes. But overhead, across millions of human lifetimes, one feature in the sky refuses to stay the same. At first, Andromeda is only a faint smudge, the kind of ghostly patch astronomers once discovered with backyard telescopes. To early observers, it is a curiosity, a fuzzy island of light beyond the familiar band of the Milky Way, nothing more. Then, almost imperceptibly, expectation meets reality. Century by century, that smudge brightens, the core sharpens, the disk widens. What once required long exposures and sensitive instruments slowly becomes a naked eye spiral. By the end of tonight, you're going to understand just how dramatic that transformation becomes. Dust lanes grow obvious, like charcoal strokes across a glowing canvas. Star-forming regions, once invisible, begin to stand out as tiny knots of blue-white fire. The solar wind still blows, the local planets still orbit, but the boundary of the familiar sky is being redrawn by a galaxy that refuses to remain a distant neighbour. Fast forward to the first close pass. Now, let's begin a true time lapse. The night is no longer dominated by a single band of stars. Two great disks overlap. One is the distorted Milky Way, its spiral arms tugged and stretched. The other is Andromeda, now so large that its arms arc from horizon to horizon. If you could compress millennia into minutes, you would see rivers of stars pulled out into tidal tails, great luminous bridges connecting the galaxies like strands of glowing silk. No one predicts how eerie it feels when the sky looks crowded, but almost nothing ever collides. Stars slide past stars with light years of clearance, guided only by gravity's invisible hand. From this world's surface, bright clumps of new star formation flare into existence as gas clouds are squeezed, while ghostly streams of orphaned stars trace sweeping curves across the heavens. Then, a pattern interrupt. After the first encounter, Andromeda seems to retreat. The sky relaxes. The grand overlap shrinks back into a warped, off-center spiral. For a few 100 million years, it almost looks like the danger has passed. But orbital dance replaces head-on impact. The galaxies loop around each other, then fall back together. Each pass more chaotic than the last, each encounter scrambling spiral arms into tangled plumes. Over billions of years, the structure that defined both galaxies dissolves. The Milky Way's elegant spiral, the classic pinwheel of Andromeda, both fade into a single, swollen glow. From the surface of that future world, the final state is overwhelming, a dense, brilliant, central region dominating the sky, not as a thin band, but as a vast, egg-shaped halo of light. No clear arms, no tidy disk, just Milkdromeda, a massive, elliptical-like galaxy, its core a blazing city of stars. Under that glow, hypothetical descendants could look up and know with the calm of long hindsight that their home is a merger. Two ancient giants, once separated by millions of light-years of space, now fused into a single system. And the real question becomes, What happens in that crowded center where those twin black holes finally meet? Those twin black holes spiraling together feel like destiny, a scripted finale. But myth number 5 says something even stronger, that the entire Andromeda Milky Way encounter runs on a fixed timetable, as if the universe quietly penciled in galactic collision for a specific Tuesday 4 billion years from now. That is not how gravity works. Predicting the future of 2 giant galaxies is closer to predicting the long-term motion of every planet in a crowded solar system. Tiny uncertainties in the starting conditions, mass, speed, direction, where the dark matter really sits, grow, orbit after orbit, into huge differences over billions of years. A fraction of a kilometre per second in velocity today can mean hundreds of thousands of light years in position when those black holes finally meet. Before we get started on Webb, it helps to see where the uncertainties come from. The first big unknown is mass. Scientists still do not know the exact masses of the Milky Way and Andromeda. Stars only tell part of the story. Most of the weight hides in dark matter halos extending far beyond the bright disks. Change those halo masses by a few tens of %, and the whole gravitational dance shifts. Then there is the shape and distribution of that dark matter. Is Andromeda's halo more concentrated, like a dense core, or puffed out and elongated? Does it have subclumps tugging on the Milky Way the way small planets tug on a spacecraft? On top of that, the local group is not just a 2-body problem. The Triangulum galaxy, M33, and a swarm of smaller companions all contribute tiny gravitational nudges that compound over cosmic time. And perhaps the most famous uncertainty of all, Andromeda's sideways or tangential velocity. Hubble and Gaia pin down a first estimate, enough to show our galaxies are approaching, but not enough to lock in a single exact trajectory. A slightly higher sideways speed can turn a head-on crash into a long, looping orbital dance. This is where Webb sharpens the picture without freezing it. By the end of tonight, you're going to understand why that distinction matters. Webb's infrared vision maps Andromeda's core and disk in exquisite detail, tracing cold dust lanes, star-forming regions, and the motions of stars buried behind veils of gas. Those motions reveal the galaxy's mass distribution, which in turn constrains the shape and depth of its dark matter halo and overall gravitational potential. The result is tighter ranges, not perfect answers. Models that once allowed wildly different futures now cluster around a narrower set. First close passage in roughly 4 to 5 billion years, but still with a spread of a few 100 million years for when that first deep encounter actually happens. The broad picture is robust, a slow approach, tidal distortion, multiple passes, eventual merger into a Milkdromeda-like system. The fine details, exact timing, angle, how many orbits before final coalescence remain fuzzy. Tonight, we're going to push against myth number 5 directly. The universe does not run on human appointment calendars. No one predicts the merger down to a specific year, and absolutely no one anticipates a single prophetic date when the sky suddenly erupts. These are probabilistic forecasts, not cosmic prophecies, and there is one more twist. As those probabilities narrow, they reveal something even stranger about the fate of our own solar system inside that evolving, merged galaxy. That twist is invisible. It doesn't shine, it doesn't glow, and yet it holds the script of this entire encounter in its silent grip. Before we get started, set aside the bright spiral arms and glowing nebulae. Those are decorations. In both the Milky Way and Andromeda, most of the mass is not stars, not gas, not dust. It's dark matter, an enormous, roughly spherical halo extending far beyond the visible disks, like a hidden scaffold. The shape and reach of those halos decide how strongly the galaxies pull on each other, how fast they trade momentum, and how quickly the dance tightens. Now, let's begin. When two massive halos move through each other, something subtle happens. Imagine Andromeda ploughing through the Milky Way's dark matter sea. As it moves, its gravity focuses some of that invisible material into a slight overdensity behind it, a wake. That wake tugs backward on Andromeda, just as a headwind tugs on a spacecraft trying to leave a planet. This process has a formal name: dynamical friction. Orbital energy is drained not by collisions of stars, but by this invisible drag in the dark halo. The same thing happens in reverse. The Milky Way carves a wake in Andromeda's halo. Two giant galaxies, each wrapped in dark cocoons, slowly spiraling together because the very medium they swim through refuses to let them glide forever. No one expects a single dramatic impact. This is a long, grinding loss of energy, written in gravity. But how do scientists study halos that cannot be seen? Tonight, we're going to follow Webb far beyond the local group, out to crowded galaxy clusters where dark matter reveals itself indirectly. In those clusters, background galaxies are stretched and warped into arcs by a phenomenon called gravitational lensing. The visible mass in the cluster is not enough to explain those distortions. The extra bending is the fingerprint of dark matter. By the end of tonight, you're going to understand why Webb's sharp infrared vision is crucial here. It resolves faint, distant galaxies whose distorted shapes map the hidden mass in front of them. In galaxy-galaxy lensing events, a single foreground galaxy acts like a magnifying glass, its halo bending light from another galaxy far behind. Webb measures how strong that bending is, how far it reaches, and how it changes with cosmic time. From thousands of these events, scientists build statistical maps of what typical dark matter halos look like. How dense their cores are, how fluffy their outskirts become, how they respond when galaxies merge. Those maps feed directly back into simulations of the Milky Way Andromeda system. The local group's halos cannot be imaged from the outside, but their behavior must follow the same physics. If Webb shows that halos in the young universe were puffier, or that cluster halos are more elongated than expected, modelers adjust the properties of our own halos and rerun the merger. The result? A gentler orbital dance, more passes before coalescence, a very different future for our solar system than a simple head-on crash. And here is the unsettling question. What if dark matter is not perfectly cold and collisionless? If it were even slightly stickier, self-interacting, or distributed in clumps instead of smooth halos, dynamical friction would change. The wake could be stronger or weaker. The spiral could tighten faster, or never quite complete. In one version of physics, the Milky Way and Andromeda fuse quickly. In another, they might only graze and drift apart. So the boundary between doomed merger and missed encounter may rest on properties of matter that no telescope can see directly. And Webb's next measurements of distant, distorted galaxies may tell whether our own future is locked in or still negotiable. So if the fate of our solar system can hinge on invisible particles and quantum fields, what about something as simple as weighing two galaxies? Myth 6 says that part is nailed down, two spirals, two numbers, done. But the moment scientists tried to put the Milky Way and Andromeda on the same scale, the picture started to wobble. Now, let's begin. For decades, the standard story went like this: Andromeda is the heavyweight, the clear champion of the local group, and the Milky Way is the understudy. Early models using satellite galaxy motions and rotation speeds often put Andromeda at nearly twice the mass. In that version, Andromeda doesn't just approach, it dictates. The Milky Way's orbit, the shared centre of mass, the violence of the eventual merger, all lean in Andromeda's favour. Then new data arrived. Gaia mapped precise stellar motions in our own halo. Other surveys tracked distant globular clusters whipping around the galaxy. Suddenly, some teams argued the Milky Way might be closer in mass to Andromeda than anyone expected, perhaps only modestly lighter or even comparable. The expectation was a clear bully and a clear victim. The reality might be two contenders circling the same ring. And while that debate played out on our side, Andromeda refused to stand still. Its mass estimate depends on how fast its disk rotates, how its dark matter halo pulls on its satellite galaxies, and how that pull changes with distance. As Webb and other telescopes trace cooler gas, dust lanes, and faint halo stars far beyond Andromeda's bright core, some earlier models that assumed an enormous dark matter envelope are being trimmed back. Less dark matter than predicted means less total mass. The boundary between dominant giant and near equal partner starts to blur. Here's the pattern interrupt. The same collision everyone talks about can look completely different just by sliding those masses around. If Andromeda really outweighs the Milky Way by a large factor, the merger is a one-sided drama. The Milky Way's disk gets flung into long tidal tails, its stars whipped around a path that orbits deep inside Andromeda's gravity well, like a smaller spacecraft falling past a massive planet. By the end of tonight, you're going to understand that this is only one possible script. Change the ratio, and the choreography changes. If the galaxies are closer in mass, the future looks less like a battering ram and more like a mutual embrace. Both disks distort. Both fling out streams of stars. Both swing around a shared centre of mass that lies in the dark space between them. No one predicts a gentle waltz, but it's no longer a one-punch knockout. Some models even allow that the Milky Way is not dramatically less massive than Andromeda at all. In those scenarios, Andromeda stops being the cosmic bully barreling in from beyond and becomes something stranger, a near twin, falling with us rather than onto us. Tonight, we're going to see that myth number 6, pretending these masses are perfectly known, is an illusion. The scales are still being calibrated, and Webb is one of the sharpest tools tightening those numbers, one rotation curve and one drifting satellite at a time, before revealing what kind of encounter really waits in the dark. Myth number 6 ends with the scales still sliding under our feet. Myth number 7 begins with something even stranger, the first true 3D map of that cosmic balance sheet. Tonight, we're going to step back and watch the local group not as a static star chart, but as a living, moving system of galaxies, halos, and invisible mass. Now, let's begin with the quiet workhorse that made this possible. Gaia is not a flashy deep space observatory. It sits in the inner solar system near the L2 point and does one thing with relentless precision. It measures where stars are and how they move. Over 1 billion stars. Positions, distances, and motions pinned down to tens of micro-arc seconds. That is like resolving the width of a human hair from several thousand kilometres away. The result is not a static map, it is a 3D movie of the Milky Way's internal dynamics. With that movie, scientists can watch the disk warp and ripple under past encounters. They can see satellite galaxies like the large and small Magellanic clouds dragging tidal streams behind them, and stellar rivers such as the Sagittarius stream wrapping around the galaxy. Those streams are not just pretty arcs in space, their shapes, thicknesses, and precession reveal how much dark matter must be present and how it is distributed, change the mass of the Milky Way's halo, or its shape from spherical to squashed, and the simulated streams twist in ways that no one expects. Gaia's data turns those streams into probes. They trace the gravitational field all the way into the outer halo, where the solar system will one day drift as the galaxy evolves. From this, teams have begun to reconstruct an entire merger history, when dwarf galaxies fell in, how hard they hit, and how their debris now orbits as ghostly currents of stars. At the same time, Gaia tracks the motions of satellite galaxies themselves, tightening estimates of the Milky Way's total mass and motion relative to the local group's centre of mass. But an interior view is only half the story. This is where Webb enters. While Gaia watches from inside the disk, Webb looks outward, resolving external galaxies that are going through the very interactions Gaia hints at. No one predicts identical twins, but Webb routinely images spirals mid-collision, halos interpenetrating, disks pulled into tidal tails, and starburst regions igniting along compressed arms. Those scenes are laboratories. They test the same physics of halos and disks that simulations apply to the Milky Way Andromeda system. By the end of tonight, you're going to understand why this pairing is so powerful. Recent studies use Gaia's refined Milky Way motion combined with updated Andromeda velocities from Hubble and Webb to rerun local group simulations. The result is a new class of models where our galaxies may not be on a simple head-on crash course, but locked in a slower orbital dance around a shared center of mass. Absolutely no one anticipates having both an interior and exterior view of galaxy dynamics in a single generation, yet here it is. For the first time, the mission to predict our fate is constrained from both sides, and the next section will show what those reimagined orbits actually mean for the night sky. That reimagined orbital dance only makes sense if you pretend the universe is clean and simple. Two galaxies, one collision, fade to black. But in real space, the Milky Way and Andromeda are not isolated dualists meeting at high noon. They are the brightest members of a crowded arena. Before we get started on the next set of orbits, there is a third giant that refuses to stay in the background. The Triangulum galaxy, M33, is the local group's quiet middle child. Smaller than the Milky Way and Andromeda, but still a full spiral system with tens of billions of stars. Observations suggest it is gravitationally bound to Andromeda, whipping around it like a companion in a wider solar system of galaxies. Some simulations even show M33 diving into the main event, either spiraling in to join the merger or getting flung out as a high-speed exile. Tonight, we're going to let that sink in. The future Milkdromeda remnant is not just a two-body problem. It is at least a three-body problem, and three-body problems are where simple orbits go to die. Tiny changes in mass, angle, or timing can redirect entire trajectories. For M33, that means a spectrum of fates merge early with Andromeda and reshape its disk, skim through the combined halo and light up new star formation, or get ejected into intergroup space as a wandering spiral. And those are only the heavyweights. Surrounding both major galaxies is a swarm of dwarf companions, dozens of faint satellites already being torn apart. Gaia has mapped their remains as ghostly stellar streams arcing through the Milky Way's halo, thin rivers of stars that trace where small galaxies were shredded by tidal forces. Andromeda shows the same scars, shells, loops, and streams that Webb and ground-based telescopes have discovered in its outskirts, evidence that this system has been dining on smaller neighbours for billions of years. These minor galaxies may look insignificant, but their collective influence is real. Each satellite carries mass. Each orbit carries angular momentum. As they spiral in, they experience dynamical friction, gravitational drag that transfers energy from ordered motion into random motions of stars and dark matter. Over billions of years, that drag subtly reshapes the paths of the Milky Way and Andromeda, changing how quickly they fall together, how much they spin, and how violently their disks are stirred when they finally meet. By the end of tonight, you are going to understand why some simulations now show M33 crashing into Andromeda before the Milky Way ever arrives, thickening Andromeda's disk, feeding its central bulge, and loading the combined system with fresh gas. In other runs, M33 plunges through during the main encounter, triggering asymmetric starbursts and leaving warped tidal tails that twist far beyond the final remnant's visible boundary. No one expects a clean, symmetrical merger after that. No one predicts a simple spiral to elliptical transformation when a third galaxy and a cloud of dwarfs are constantly pushing and pulling on the system. The myth of two lonely giants on a fixed collision course falls apart. Our fate is being written by an entire community of galaxies, each adding a small gravitational nudge. The next question is obvious. When all of those nudges add up, what does the final sky actually look like from inside the chaos? So, when all of those nudges add up, the scene that emerges is not a single cataclysmic smash, but a choreography. Tonight, we're going to rewrite the script from galactic collision to orbital dance. And the new version is stranger, slower, and far more elegant than the old doomsday headline. First, the corrections. The classic picture was simple: Andromeda as a cosmic battering ram aimed straight at the Milky Way on a perfectly head-on trajectory, destined to destroy our galaxy in one apocalyptic impact. Reality is subtler. New Gaia and Webb-informed models show an encounter that is likely off-axis, not a bullseye. The galaxies will be violently reshaped, but not literally destroyed. Stars almost never collide, because the space between them is enormous compared to their size, and the whole process does not happen in one night of cosmic violence, but over multiple passes spread across billions of years. Now, let's begin to picture the new consensus. Andromeda and the Milky Way are not two strangers meeting for the first time. They are already bound, orbiting a shared centre of mass buried somewhere in the dark between them. Their extended dark matter halos overlap right now, invisible cocoons sliding through each other as both systems plough through the local cosmic wind. As they orbit, dynamical friction, gravitational drag from all those stars, gas clouds, and dark matter particles bleeds orbital energy away and slowly tightens the embrace. The sequence that follows looks less like a crash and more like a slow-motion flyby that refuses to end. In roughly 4 billion years, the first close pass pulls out immense tidal tails, stretching streams of stars and gas, tens of thousands of light-years into intergalactic space. Gas clouds compress, shock fronts ripple through the disks, and star formation surges in bright, short-lived starburst regions. Then comes the pattern interrupt. Instead of merging on the spot, the galaxies swing past each other and partially separate, distorted but still distinct, arcing out on a wider loop before gravity reels them back in. Each subsequent pass digs deeper. Tidal forces further scramble spiral arms, fling stars onto elongated orbits, and mix the outskirts of both systems into a shared stellar envelope. Over several orbits, the disks puff up, the original structures dissolve, and the two galaxies finally settle into a single, more spheroidal remnant that some scientists nickname Milkdromeda. The solar system will likely be carried along, not shattered, its trajectory reshaped, its night sky transformed, but its planets still bound to their star. Here is where Webb matters. By the end of tonight, you're going to understand that its role is not one dramatic measurement that flips a yes-no switch on collision. Instead, Webb refines the mass distribution in Andromeda's bulge and halo, maps cold dust and star-forming regions, and observes real mergers in other galaxies at high resolution. Each observation is a constraint on how gas responds to tides, on how long starbursts last, on how quickly orbits decay. No one expects a single spectrum to rewrite the fate of the local group, but a suite of precise measurements can. This is a scientific upgrade. The old Andromeda will destroy the Milky Way line was a useful first-order story, like drawing the heliosphere as a neat bubble before spacecraft discovered its true distorted boundary. Now Webb, paired with Gaia, is giving a high-definition version where the choreography, off-axis passes, tidal bridges, starburst knots, matters as much as the final merged remnant. The next step is to zoom into that choreography and ask, from the surface of a planet, what does this orbital dance actually look like, night after night, over millions of years? From that wide-angle choreography, Webb does something no previous mission could. It dives straight into Andromeda's heart. Tonight, we're going to stand, figuratively, right above its central bulge and watch the core of our nearest giant neighbour resolve from a hazy glow into a crowded, gravitational city of stars. In optical light, Andromeda's centre looks almost featureless, a bright smear, a saturated core, not much detail, but that's an illusion created by dust and distance. Webb's infrared eyes cut through that dust, peeling back the dark lanes that slice across the inner disk and exposing the true structure underneath. Suddenly, what looked smooth becomes granular. Dense star fields, overlapping clusters, and filaments where gas, dust, and stars braid together under the pull of the galaxy's central mass. The contrast between expectation and reality is brutal. Astronomers once treated the bulge as a single, simple component in the model, a rounded pile of old stars, a convenient approximation for the inner gravitational potential. Webb shows a layered system instead. There are ancient, reddish stellar populations packed like a solid, almost continuous background. Threaded through them are younger, bluer in infrared stars tracing spirals and arcs that twist toward the centre. By the end of tonight, you're going to understand why that mix matters for the Milky Way's future. Infrared is the key. Dust that blocks visible light becomes almost transparent at Webb's wavelengths, so the core stops being a glare and starts being a map. The telescope can separate stars by colour and brightness, which, in galaxy work, means by age and mass. It can also trace subtle elongations in the inner light, revealing whether Andromeda hides a central bar structure, an elongated bar of stars that can funnel gas inward, feed the central black hole, and reshape the inner disk over billions of years. Brightness is not just pretty, it is physics. The way light falls off from the centre, the clumpiness of the bulge, the ratio of old to young stars, Those are inputs to stellar population models that convert photons into kilograms. From Webb's images, scientists derive how much stellar mass is crammed into the inner few thousand light-years, how steeply that mass rises toward the black hole, and how smoothly it connects to the surrounding disk. That mass profile feeds directly into the gravitational potential used in encounter simulations. And then there are the scars. No one predicts a galaxy as massive as Andromeda to have a perfectly calm core. Webb finds hints of disturbed structures, asymmetries, off-center star clusters, and pockets of unusually metal-poor or metal-rich stars that do not fit a single, quiet formation history. These are signatures of past mergers. Smaller galaxies that plunged in were shredded and left their stars embedded in the bulge like fossil currents in a riverbed. Those fossils matter because past mergers change how a galaxy responds to future encounters. A core puffed up by previous impacts is more resilient. A core still settling can slosh and ring when tugged. Webb's refined central mass and structure tell simulators how rigid Andromeda's inner regions really are and how easily its orbits can be torqued when the Milky Way's gravity sweeps past. No one expects the word destroy to survive contact with that level of detail. The next step is to take this updated mass map and watch how it rewrites the orbits of stars, including ones like the Sun, as the long encounter unfolds. That mass map is the blueprint for the encounter. But to see how Andromeda will actually fight or dance with the Milky Way, you have to step outside the bright disk and into something far stranger, the halo. Now, let's begin. Picture Andromeda not as a flat spiral of stars, but as a glowing island wrapped in a vast, ghostly envelope. This stellar halo is a huge, faint sphere of old stars, globular clusters, and razor-thin tidal streams stretching hundreds of thousands of light-years beyond the obvious spiral. Ground-based surveys and Hubble have already traced some of these filaments in exquisite detail, like chalk lines left after a cosmic collision. Those lines are not decorative. They are the shredded remains of smaller galaxies Andromeda has already consumed. Each stream is a former dwarf system, pulled apart by tidal forces, its stars stretched into long arcs that still remember the orbit they once followed. Together, they form a fossil record of Andromeda's past mergers and of how its invisible dark matter halo grew by swallowing neighbors over billions of years. By the end of tonight, you're going to understand why those faint scars matter for the Milky Way's future. The more streams you see, the more violent the diet. The wider they spread, the more extended the dark halo must be. That's because only a massive, far-reaching gravitational field can tear a companion into a stream and still keep its stars bound in a slow, looping orbit. This is where Webb steps in. Hubble and ground telescopes mapped the brightest traces. Webb can dive deeper into the outskirts where the light is thin, the stars are red, and the dust is cold. Its infrared vision cuts through obscuring dust and crowding, resolving individual ancient giants that were invisible before, especially in regions where the disk and halo overlap and confusion used to dominate. Suddenly, streams that looked smooth begin to break into substructure. Clumps of stars reveal separate merger events. Subtle color differences expose different ages and chemical fingerprints, telling scientists which pieces came from which swallowed galaxy. No one expects that level of detail from the faintest edges of a galaxy 2.5 million light-years away. But Webb's sensitivity pushes that boundary outward, and the shape of the halo is not just a historical curiosity. a more extended, massive halo, means Andromeda's gravity reaches farther into intergalactic space, tugging on the Milky Way long before the disks ever touch. That changes the orbital choreography. How quickly the galaxies fall together, how much they swing past, how many times they loop before settling into a merged system. Here's the symmetry. By reading the scars of Andromeda's past mergers in its halo, scientists are learning how it behaves during close encounters, how it strips, warps, and absorbs. Those same rules will govern its final major merger, with us. The mission now is to feed those newly mapped streams into simulations and see whether they predict a gentle orbital dance or something no one predicts. Because there is one more component lurking in the dark that could still rewrite the script. That hidden component is gas, cold, turbulent, easily pushed around by gravity and shock waves. And when galaxies collide, that gas doesn't just drift, it ignites. When two massive disks pass through each other's gravitational fields, their gas clouds feel tidal forces the way oceans feel the moon, pulled, stretched, then slammed together. Collisions between clouds drive shocks through the interstellar medium, compressing regions that were once too diffuse to form stars. A quiet spiral can turn into a starburst galaxy, its star formation rate jumping by a factor of 10, 100, sometimes more, for a brief, furious phase in its life. Tonight, we're going to let Webb show what that really looks like. Invisible light, interacting galaxies like the antennae or the mice look chaotic, but almost delicate. Long tidal tails, faint bridges, warped disks. In the infrared, Webb strips away the illusion. Those graceful arcs explode into bright, knotty clumps, compact, star-forming regions where newborn clusters are still wrapped in cocoons of dust. The dust that hides them in optical telescopes glows fiercely in Webb's wavelengths. Now, let's begin with a pattern interrupt. On screen, picture what looks like a single, smooth spiral arm. Zoom in with Webb's resolution and it shatters into hundreds of blazing knots. Each knot is not one star, but thousands. Each is a city of suns forming inside a collapsing gas cloud, driven there by the violence of a galactic encounter. Scientists use those Webb images as both a catalogue and a calibration tool. Measure how dense the gas is, how fast it's moving, how strong the shocks are, and then feed those numbers into simulations of galaxy mergers. The mission is not just to admire pretty pictures, but to extract the physics. How much gas is converted into stars, how quickly, and where in the system those bursts peak. Run that same physics forward for the Milky Way Andromeda encounter, and a clear pattern emerges. The first close pass, several billion years from now, is when the real firestorm begins. As their disks overlap, gas in both galaxies is stirred, compressed, and funneled toward their centers. Simulations predict rings and arcs of intense starbirth, lighting up the overlapping regions, echoing the starburst knots Webb has already discovered in more distant collisions. By the end of tonight, you're going to understand why this is not only an ending. By the time that first pass happens, the sun is an aging star, long past its prime. But around it and far beyond it, new generations are just beginning. Massive clouds torn from both galaxies will collapse into fresh clusters, fresh planetary systems, fresh chances for habitable worlds. No one expects a word like merger to also mean rebirth, but on galactic timescales, that's exactly what it is. And as Webb surveys starbursts across cosmic time, from nearby collisions to mergers billions of light-years away, it is quietly building the backbone of our own forecast. because to know how our night sky will transform, the next step is to ask what happens to those newborn stars once the chaos settles. Those newborn stars are only half the story, because buried deep in the hearts of both galaxies, something far darker is waiting to dance. Before we get started, zoom all the way into the Milky Way's centre. There sits Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. And in Andromeda's core, another giant waits, even heavier, weighing in at hundreds of millions of solar masses. Right now, both are quiet by quasar standards, sipping gas at low rates, their influence felt more through gravity than through light. Tonight, we're going to follow those giants into the future collision. In a major merger, galaxies do not just blend like clouds. Their most massive components sink. As the Milky Way and Andromeda interpenetrate, dynamical friction, the drag from billions of stars and dark matter particles, robs the central black holes of orbital energy. Prediction meets reality. Simulations show them spiraling toward the common center, from tens of thousands of light-years apart to just a few. At that point, the two no longer behave like separate monsters. They become a bound pair, a supermassive binary black hole, orbiting each other inside the merged Milkdromeda galaxy. Their dance tightens, gravitational waves carry away angular momentum. The orbit shrinks from light-years to parsecs, to fractions of a light-year, until the only way out is in. No one expects that final plunge to be gentle. By the end of tonight, you're going to understand why this is one of the loudest events in the universe, and yet almost invisible in normal light. Webb does not detect gravitational waves. That job belongs to detectors like LIGO and Virgo for stellar mass mergers. But Webb does something just as crucial. By resolving active galactic nuclei and even dual AGN in merging systems, two bright cores in the same distorted galaxy, it identifies the stages leading up to black hole coalescence. Those are snapshots of our own future, taken in other corners of space. The next leap comes from missions that do not yet exist in the sky. The planned LISA spacecraft will fly in a vast triangle millions of kilometres across, tuned to the low-frequency gravitational waves from supermassive black hole mergers. Where Webb maps the gas, dust and stars, LISA will listen to the ripples in space-time itself, potentially catching events very much like the Milky Way Andromeda merger long before ours happens. This sounds apocalyptic. Two black holes, millions of suns each, colliding. But here is the pattern interrupt. For stars out where the sun orbits, the danger is minimal. The energy is enormous, yet it is focused into gravitational waves that stretch and squeeze space-time rather than into a blast of destructive radiation across the whole system. The main fireworks play out in the inner light year or so, where orbits are scrambled and some stars are flung out as hypervelocity runaways. From our distant vantage point, the merger would be a change in the background, not an instant catastrophe. The night sky would evolve, not explode, and the real question becomes, how does that slow transformation reshape the long-term future of our solar system itself? That slow transformation ends with something new in the sky, not the Milky Way, not Andromeda, a single enormous hybrid that astronomers already nickname Milkdromeda. Tonight, we're going to stand inside that future galaxy and ask, what does the final result of this cosmic mission actually look like? Simulations of the merger tell a clear story. Two grand design spirals go in. One swollen, smooth system comes out. By the end of tonight, you're going to understand why the elegant spiral arms vanish, replaced by a galaxy that's more elliptical or lenticular, an immense rounded glow with only a hint of a disk and a central region so bright it outshines everything around it. The orbits of billions of stars get scrambled, trading ordered rotation for a puffed-up, three-dimensional swarm. To picture it, you do not have to imagine blindly. Webb has already shown you Andromeda's cousins. In deep infrared images of massive ellipticals and late-stage merger remnants, the structure is unmistakable. Smooth light distributions with no sharp spiral pattern, extended halos that fade slowly into the dark, and delicate shells and ripples where past collisions left frozen interference patterns in the stars. Those faint arcs, barely above the background, are the fossil waves of earlier encounters. Some of Webb's targets are especially eerie analogues. Two once-spiral galaxies locked together, their original disks shredded into a single, rounded core, wrapped in tidal debris. The gas has been driven inward. The star-forming knots glow in infrared-like embers. Andromeda is expected to follow that script. A huge blended bulge, a thickened disk or lens, and a halo stretched far beyond what either progenitor owned alone. Inside that final form, the stellar population will carry a layered memory of the collision. Old red giants from the Milky Way's thick disk, ancient halo stars from Andromeda, and younger, metal-rich stars born in violent starbursts as gas clouds crashed and compressed. Their chemical fingerprints, ratios of elements forged in different generations of supernovae, will separate family trees long after the original spiral shapes are gone. Future scientists will read those patterns like DNA. The invisible architecture grows even more dramatic. The merged dark matter halo will be vast, enveloping not just Andromeda's stars, but many of the surviving satellites from both galaxies. What used to be a small group dominated by two large spirals becomes a single, heavyweight, central galaxy, anchoring the local group's future and setting the gravitational boundary for hundreds of thousands of light years. From the inside, though, the story changes. Before we get started on the fate of the solar system, pause and imagine being a distant descendant looking up from some surviving planet. No one expects to see a Milky Way band and an Andromeda oval. No one predicts two separate islands of light. There is only one colossal, hazy glow overhead, and the idea that it was once two galaxies is an abstract reconstruction, a triumph of stellar archaeology rather than direct observation. But that raises a sharper, personal question. In that enormous, tranquil-looking Andromeda, where does our tiny solar system actually end up, and does it still have a home at all? For years, that question came with a ready-made headline: Andromeda will destroy the Milky Way, full stop. It sounded like a date stamped on the end of the solar system, a cosmic eviction notice with nowhere to go. But what does that claim actually mean when it is unpacked? First, a nearly head-on trajectory. Two spiral galaxies racing toward each other like colliding cars. Second, catastrophic structural loss, disks shredded, spirals erased in a single, violent impact. And third, the implied annihilation of stars and planets, as if worlds would routinely slam together and vaporize. Now, let's begin. Webb's view of Andromeda does not deny the encounter, it rewrites the choreography. By tracing cold dust lanes, star-forming regions, and the dense stellar traffic in Andromeda's bulge and halo, scientists can weigh the galaxy more precisely and track how its mass is actually distributed. When that is folded together, with Gaia's stellar motions and earlier Hubble measurements, the picture shifts from a straight-in collision to a slower, more intricate orbital dance. Designed as a simple doom prediction, it is turning into a multi-act mission in deep time. No one expects a single apocalyptic smash. Instead, simulations that match Webb's refined mass and structure show repeated close passes, tidal stretching, and long filaments of stars pulled into space. The galaxies do not explode, they interleave. Here is the pattern interrupt. In a galaxy collision, almost nothing collides. The average distance between stars is so enormous that even when two entire systems pass through each other, direct star-star impacts are vanishingly rare. Gravity does nearly all the work. It bends orbits, sculpts tidal tails, compresses gas into starburst regions, and slowly erases the clean spiral outlines both galaxies started with. By the end of tonight, you're going to understand that the Milky Way is still doomed in one sense and astonishingly safe in another. The identity as a graceful spiral will end, the disk will thicken, the arms will smear out, and a new, more massive, more rounded Milkdromeda will emerge. Yet the overwhelming majority of stars, including, according to current simulations, our Sun, will simply be reassigned to new orbits, drifting farther from the galactic centre, but remaining intact. So, what did Webb really destroy? Not the Milky Way. It helped destroy a lazy metaphor. The old story of a single cinematic crash gives way to a scientifically richer narrative, a drawn-out interaction, evolving gravitational boundaries, and a sky that changes over billions of years, not in one catastrophic night. Tonight, we're going to treat that as a victory for science literacy. When new data arrives from Webb, from Gaia, from future spacecraft that may one day cruise beyond our merged galaxy's halo, the story will change again. That is not scientists being wrong in some trivial sense. That is the mission of science doing exactly what it is supposed to do, replacing fear-shaped guesses with measured, testable, astonishing reality. And if the fate of the whole galaxy can be rewritten that dramatically, what does that say about the smaller fate of one yellow star and its planets inside it? So when a telescope like Webb walks in and casually rewrites the fate of two galaxies, headlines do what headlines always do. They go hunting for doom. Andromeda on collision course with Milky Way. Our galaxy is doomed. Andromeda will slam into and destroy the Milky Way. You have seen versions of those banners for more than a decade. Now compare that to the original Hubble work from 2012. The papers talk about proper motion constraints, a likely merger within 4-6 gear, and a range of plausible encounter geometries. The language is careful. Probabilities, time windows, model assumptions. No one predicts galactic demolition day on June 3rd, 4 billion years from now. That gap is not an accident. It is an incentive problem. Dramatic, absolute language drives clicks and views. Slam, destroy. Apocalypse, compress a messy, a high-dimensional orbital calculation into a single, emotionally loaded verb. The nuance that scientists live inside every day, error bars, uncertainties, caveats, gets stripped away because it slows the scroll and softens the fear. Tonight, we're going to use Andromeda as a case study in how that happens. A first-generation result. Hubble's measurement of Andromeda's sideways motion was always framed as a best estimate. It said the galaxies were likely on a nearly head-on path, that their halos were already interacting, that a merger was probable on multi-billion-year timescales. Within the community, that was a starting line, not an ending. But once that picture hit the media, the story hardened. Head-on became guaranteed, probable became inevitable. A gentle, drawn-out gravitational waltz became a fiery car crash in space. And then, for years, every new mission, every new simulation, every new hint from Gaia or ground-based telescopes was plugged back into that same pre-written script. Yes, we're still doomed. By the end of tonight, you're going to understand why Webb's refinements feel so shocking in that context. Not because the science took a wild turn, but because the public story was frozen while the actual models kept moving. No one expects the popular narrative to be the least accurate part of the whole system, but here, that is exactly what happened. So how do you protect yourself the next time a headline announces that some planet, black hole or rogue galaxy is coming for the solar system? Before we get started panicking, look for three things. First, uncertainties. Are there ranges, confidence levels, alternate outcomes? Second, scenarios. Do scientists describe multiple possible futures or just one cinematic ending? Third, data. Is a new instrument like Webb refining an older result or truly overturning it? If those pieces are missing, you are not reading science. You are reading a pitch. The mission of this channel is to bridge that gap, to go past the banner and into the paper, to turn the messy, iterative process of discovery into a narrative that respects both your curiosity and the data. And in the next section, that is exactly what will happen to the word collision itself. So when the word collision gets demoted in the next section, it is not just a vocabulary fix, it is a diagnostic. Tonight, we're going to use the fate of the Milky Way as a stress test for everything thought to be known about gravity, dark matter, and how galaxies grow. If scientists cannot predict what two gigantic galaxies in our own neighbourhood are going to do over the next few billion years, then every confident claim about galaxies 10 billion light-years away is on probation. The same equations of motion, the same dark matter halos, the same gravity that are supposed to explain Andromeda's future are also being used to interpret faint smudges in Webb's deep fields. Get the local test wrong, and the distant universe becomes a house of cards. Now, let's begin with the bridge between future merger and early universe. The simulations that show the Milky Way and Andromeda orbiting, spiraling, and eventually blending into Milkdromeda are not one-off movie renders. They are the exact same numerical engines used to rewind cosmic history, to ask how the first large structures assembled from tiny density ripples after the Big Bang, how small proto-galaxies crashed together, and how the cosmic web emerged. When Webb discovers a warped, clumpy galaxy, only 500 million years after the Big Bang, those merger codes are the only way to decide whether that object is normal or a problem for current models. The connection goes even deeper. To refine Andromeda's true motion, missions like Gaia measure micro-arc-second shifts in star positions. Webb maps coal dust and star-forming regions in Andromeda's disk and bulge. Feed that into a simulation and out comes a future timeline. But the same detectors, the same data pipelines, and the same algorithms that track those motions are now being reused in places that have nothing to do with space. Adaptive optics methods show up in retinal imaging. Compression schemes for spacecraft telemetry get repurposed for Earth observation satellites, and denoising algorithms built for faint galaxies help in medical scans and climate models. No one expects a project meant to weigh dark matter halos to improve how a tumour is seen on an MRI. No one predicts that a mission built to map the solar neighbourhood will sharpen weather forecasts. And absolutely no one anticipates that debugging a galaxy merger simulation will lead to new tricks for training neural networks on massive, messy data. There is also a quieter philosophical shock. By the end of tonight, you're going to understand that the Milky Way is not a permanent backdrop. It is a phase. The spiral arms, the familiar band of light across the sky, even the separation between our galaxy and Andromeda are temporary features in a long chain of mergers. Knowing that the future is to blend into something larger forces a different perspective on identity and permanence. What does it mean for a solar system or a civilization to belong to a galaxy whose very shape is negotiable? And this is why the Andromeda story matters now. It is not a trivia fact about the year 5 billion something. It is a live experiment in whether current theories of gravity, dark matter, and structure formation can survive contact with precision data. In the next section, when the word collision gets replaced with something much stranger, the real question will not be what happens in the far future. It will be, what does that new word quietly reveal about the universe right now? So when the word collision quietly gives way to something stranger, it helps to remember where this story started. For years, the headline was simple. Andromeda is a cosmic battering ram aimed straight at the Milky Way, on track to smash through our galaxy in a single catastrophic impact about 4 billion years from now. Designed as a clean narrative, galactic doom on a schedule. Reality did what it always does. It became messier and far more interesting. Early Hubble measurements of Andromeda's motion really did suggest a nearly head-on encounter with very little sideways drift. That fed the image of two spirals rushing together like cars on a collision course. But as more precise data arrived from Gaia, from radio arrays, and now from Webb, that straight line began to bend into an orbit. Tonight, we're going to hold both versions in mind for a moment. The old battering ram and the new off-axis dance. The main corrections are surprisingly concrete. Updated motions show that Andromeda is not plunging directly into the Milky Way. It's coming in with a sideways component enough to loop, overshoot, and return. Galaxies in encounters like this are not annihilated. They are transformed, stretched into tidal tails, compressed into starburst regions, and eventually relaxed into a new, larger system. Inside that drama, stars almost never collide. The average separation between stars is so large that even when two galaxies interpenetrate, gravity does the work at a distance. Simulations now suggest the Sun is unlikely to be destroyed. Its orbit will be torqued, flung outward into a different track around the combined mass, but the solar system remains a coherent island of planets in a changing sky. And the timeline is no longer a sharp 4 billion year countdown. It's a range of first pass, second pass, and final coalescence smeared over several billion years with real uncertainty. Webb's role in this rewrite is surgical. It refines Andromeda's mass and structure by mapping coal dust, hidden star-forming regions, and the crowded core that ground-based telescopes could not resolve. It provides living examples of mergers in progress, where off-axis encounters, multiple passes, and long tidal bridges are not rare exceptions, but the rule. Those images feed the simulations, and those simulations now favour a multi-pass orbital dance, rather than a single head-on crash. Pattern interrupt. If the word collision is misleading, what about destruction? No one expects that to survive either. Across 7 myths, the narrative has already been dismantled. Not every star will slam into another. Not every planet will be ejected. Not every orbit is doomed. The Milky Way's edge is not a hard boundary about to be shattered. It is a flexible, evolving region that has already merged with smaller galaxies many times. By the end of tonight, you're going to understand that this evolution of the story is not a failure of prediction. It is the scientific method doing exactly what it should as new data arrives. Now, let's begin the final step, rebuilding a clear, accurate mental model of where our galaxy ends, where Andromeda begins, and what their long, shared future really looks like. For the solar system, the word edge used to sound simple. You fly past the last planet, the wind from the sun dies out, and that's it. Then voyage across one invisible line after another. Termination shock, heliosheath, heliopause, and scientists realized the boundary was not a wall. It was a layered, shifting transition. Tonight, we're going to apply that same mental upgrade to the Milky Way itself. Before we get started, forget the picture of a flat spiral with a hard rim floating alone in space. In one sense, the Milky Way ends where the bright stellar disk thins out into the halo, where the density of stars drops from crowded city to cosmic countryside. In another, more physical sense, it ends where its dark matter halo stops dominating the local gravitational field and the broader local group takes over. And in a third, more dramatic sense, it ends when the spiral pattern that defines Milky Way is erased in the merger with Andromeda. Expectation? A clean border. Reality? Nested, overlapping spheres of influence. Stars in the thin disk, globular clusters in the halo, invisible dark matter reaching hundreds of thousands of light years beyond what any telescope can see. By the end of tonight, you're going to understand that when someone asks, "Where does our galaxy end?" the only honest answer is, "Which boundary are you talking about?" Here is where Webb and Gaia quietly rewrite the mission profile. Their ultra-precise measurements of stellar motions in both galaxies show that dynamically the Milky Way is not an isolated spacecraft cruising through calm space. It is already inside a shared gravitational system. The dark matter halos of the Milky Way and Andromeda most likely overlap right now, forming a combined potential well that is steering every star, every planet, every cloud of gas in the local group. No one expects a collision to begin before the disks touch. No one predicts a merger, while the night sky still looks familiar. But the data say the process is already underway at the level of invisible mass and slow orbital choreography. The local group is evolving toward a future where one giant blended galaxy, often nicknamed Milkdromeda, will dominate, and the smaller companions will be swept into that structure. So here is the mental model. Do not think of the Milky Way as a permanent island. Think of it as a phase in a long transformation, the way a young spiral grows, interacts, and is eventually folded into a massive elliptical. The Andromeda encounter is not a sudden apocalypse. It is the central act of a multi-billion-year story that has already begun. And this changes the emotional boundary as well as the scientific one. Earth is not riding a doomed ship waiting to be shattered by incoming planets. The space between stars is so vast that direct impacts are vanishingly unlikely. Instead, the solar system orbits quietly inside a living, evolving cosmic ecosystem where galaxies exchange mass, angular momentum, and light over unimaginable timescales. In the next section, this abstract future becomes personal. What the sky will actually look like and what happens to the sun when the spiral we know dissolves into something new. So now, take that quiet, evolving ecosystem and drop a civilization into it that never blinks. A species that solves extinction-level problems not once, but over and over. They migrate worlds, redirect asteroids, tap entire stars for power, and treat 1 billion years the way you treat a long-term mission plan. Tonight, we're going to stand with them, Picture their sky a few billion years from now, Andromeda no longer a faint smudge, but a sprawling, structured presence. First, the disk stretches across a patch of darkness, then it doubles, triples, until its spiral arms rival the Milky Way's band itself. By the end of tonight, you're going to understand that for a civilization prepared for deep time, this is not a doom countdown. It is an engineering opportunity and a cultural revolution. Before we get started, anchor this in the physics. Simulations using Hubble, Gaia, and now Webb data agree on key points. The galaxies will interpenetrate, tidal tails will fling stars into elongated streams, and vast starburst regions will ignite as clouds collide and compress. The solar system, if it still exists, is overwhelmingly likely to thread those changing gravitational fields without a single planet-planet impact. The environment changes, the boundary conditions of their existence shift, but space does not become uninhabitable, it becomes more diverse. That far future civilization knows this. So, they ride the merger. They seed observatories along tidal streams using those elongated arcs of stars as interstellar highways where relative velocities and gravitational assists make crossing tens of thousands of light years cheaper than ever. They identify newborn clusters in starburst knots, worlds circling stable, metal-rich suns, and reserve them the way early explorers once marked promising coasts on a map. No one expects the real headline, though, to be quiet. Deep in the coalescing core, the Milky Way's central black hole and Andromeda's giant meet in a slow, relativistic dance. For them, this is a once-in-a-cosmos event. Whole fleets of spacecraft hover at safe remove, watching space-time itself ring like a bell as gravitational waves roll out. Instruments tuned far beyond anything today record the merger, the way ancient astronomers once recorded eclipses, as sacred data. Culture adapts just as aggressively as technology. Old constellations dissolve as the familiar spiral structure stretches into arcs and shells. New myths arise around twin galactic ghosts crossing the sky, then fusing. Poets talk about living inside a time lapse, where the backdrop of existence refuses to stay still. Philosophers grapple with a simple, disorienting fact. The home galaxy is gone, replaced by Milkdromeda, a hybrid that makes previous identities feel provincial. Yet their response is not fear, it is alignment. They start to see themselves as one transient phase in a much larger cycle of assembly, collision, and renewal. The same way you learn to think of continents drifting and climates shifting, they learn to think in units of galaxy lifetimes. And here is where the thought experiment loops back to now. No one predicts that humanity, specifically, will be there. Absolutely no one anticipates a guaranteed future across 5 or 6 billion years, but the environmental conditions, enhanced star formation, altered skies, a merged galactic core, are not fantasy. They are robust predictions from current models, cross-checked by Hubble's proper motions, Gaia's stellar cartography, and Webb's infrared view into Andromeda's dust-enshrouded regions. Scientific understanding, in other words, is already extending the range of futures you can even imagine. Not just apocalypses, but awe-filled adaptations. Not just destruction, but repurposing. The real twist comes when those futures start feeding back into the present, when thinking like Milkdromeda engineers changes how you look at the next century. Because if a galaxy merger can be turned into an opportunity, what does that say about the smaller collisions coming much sooner? Those smaller collisions coming sooner. They're not just about planets or technology. They're echoes of a process that has been running since the universe was young. To see our future with Andromeda clearly, you have to zoom out until the Milky Way is just one frame in a much longer cosmic time lapse. Now, let's begin. In Webb's deepest fields, where a patch of sky smaller than a grain of sand on your arm explodes into thousands of galaxies, scientists are watching the early universe in mid-construction. Galaxies there are clumpy, misshapen, torn by tidal bridges and tails. Many are not single, serene systems at all, but swarms of fragments in the middle of merging, fed by cold gas streams and constant accretion. In that era, collisions are not rare events. They are the default. The universe is smaller, matter is packed more tightly, and gravity has less distance to work with. When two young galaxies slam together, their gas clouds crash, compress, and ignite. Star formation spikes into furious starbursts. Black holes at their centers gorge on inflowing material, lighting up as quasars that can outshine entire clusters of planets and stars. Contrast that with our situation. By the end of tonight, you're going to understand that the Milky Way-Andromeda merger is late to the party. The gas has thinned, the easy fuel is mostly gone, and both galaxies are more settled, with well-formed disks and older stellar populations. The prediction was a single catastrophic impact. The reality is a long, relatively gentle orbital dance that trades violent starbursts for slow reshaping. Here's the pattern interrupt. In one Webb field, you can watch all of this at once. Galaxies at high redshift show the chaotic youth of systems like ours. Closer galaxies at lower redshift reveal more ordered spirals beginning to interact. And sprinkled throughout are massive, smooth, red ellipticals, the end products of repeated mergers, where star formation has shut down and the remaining stars drift in a relaxed, featureless halo. No one expects a telescope to become a time machine, but Webb's infrared vision turns distance into history. Some galaxies in its images are rough analogues of the Milky Way's past. Others resemble simulations of our future Milkdromeda, swollen, redder, less structured, sitting in a halo of dark matter that has cannibalized smaller neighbors. In dense regions, clusters where thousands of galaxies share the same gravitational well, these giant ellipticals dominate. That is not an accident. Hierarchical structure formation predicts it. Small systems merge into bigger ones. Cold gas is used up or heated. The universe drifts from clumpy, blue, star-forming disks toward larger, red, quiet giants. Milkdromeda will just be one more of those giants, one more red behemoth in a universe that is gradually trading drama for stability. No one predicts it will be special to the cosmos, but it will be deeply personal to this solar system. Tonight, we're going to use that perspective as an anchor. Our merger is not an exception. It is a typical step in a long trend toward larger, more relaxed structures. And that raises a sharper question for what comes next. If our galaxy's fate is ordinary, which part of it do you actually want to inhabit? So now you're in a different place than when this mission through galactic time began. You no longer hear Andromeda will destroy the Milky Way as a simple doom prophecy. You hear it as a compressed headline for a far more intricate, evolving scientific narrative, one that has been reshaped again and again by Webb, by Gaia, by Hubble, and by a fleet of observatories quietly mapping the space between the planets and the space between the galaxies. The original plan is simple. Two spiral galaxies on a collision course, a head-on smash, an inevitable wreck. Reality is stranger. The encounter is now likely off-axis and orbital, a long gravitational dance rather than a single catastrophic crash. By the end of tonight, you're going to understand that this is not an apocalypse story. It is an engineering diagram of how large-scale structure in the universe actually relaxes over time. You now know the core moves in that diagram. Galaxies are transformed, not annihilated. Their disks warp, their halos interpenetrate, their spiral arms stretch into tidal tails, and waves of new stars ignite in compressed clouds. But the stars themselves almost never collide, because the average distance between them is so large that even in a collision, they pass like ships in a vast, dark ocean. No one expects that phrase galactic impact to hide such a quiet reality at the scale of individual suns. You also know where the real danger lies for Earth. It is not Andromeda's approach. The sun's own evolution, swelling into a red giant long before the merger finishes, is the dominant threat to this solar system. The galaxy can twist, shear, and merge around it. The local boundary that matters for life here is the changing radius and luminosity of one star. Underneath all of this, you've seen the invisible machinery, dark matter, halos overlapping, dynamical friction slowly draining orbital energy, the Milky Way and Andromeda spiraling inward through a medium that cannot be seen directly, but whose gravity sculpts the entire mission profile of their future encounter. And you understand what Webb actually contributed. Not a single dramatic press conference twist, but a set of refinements. Sharper maps of Andromeda's core, better constraints on its mass, cleaner views of dust-hidden star-forming regions, and comparisons with other merging systems that act as time-shifted analogues of our fate. Piece by piece, those measurements bend the trajectory from a simple head-on crash toward a gentler, more orbital scenario. That means you can now read headlines about our doomed galaxy differently. You can see the myths, the oversimplifications, the difference between early, first-order models and the high-definition simulations that fold in Webb, Gaia, and beyond. No one predicts every detail correctly, and absolutely no one anticipates how quickly new data can rewrite the script. Tonight, we're going to treat that as your passport. You are no longer in the crowd that just repeats, Andromeda will collide with the Milky Way. You can explain how, when, and what that really means. Now, let's begin to ask a harder question. If you understand the choreography, where in that future galaxy would you choose to stand? Where would you choose to stand when the sky itself is changing shape? That question sounds like fear at first, a survival instinct, a reflex that wants to know where the danger is. But watch what just happened to that fear. It started with a headline about destruction, a future where Andromeda slams into the Milky Way and tears the galaxy apart. And it ended with orbits, simulations, and a slow, majestic reshaping of space that plays out over billions of years. The same event, two stories, one drenched in dread, one lit by understanding. This is the quiet revolution missions like Hubble, Gaia, and Webb have pulled off. Fragile spacecraft, thin metal skins, electronics that would embarrass a modern phone, flung into the harshest environment there is, designed for a handful of years, operating well beyond their warranty. No one expects a 5-year design to still be rewriting galactic history decades later, but here we are. Hubble tracked Andromeda's sideways drift against background galaxies and turned a vague collision someday into a precise orbital forecast. Gaia mapped the motions of more than 1 billion stars in the Milky Way, giving scientists the local gravitational field in exquisite detail. Webb now peers into Andromeda's dust-choked core and faint outer halo, refining its mass, its orbit, and the way its stars move in 3 dimensions. Each mission pushes the boundary a little farther. Each one takes a fear-laden myth and replaces it with a testable story. By the end of tonight, you're going to understand that this is what science really does. It does not promise safety. It promises clarity. It turns a looming featureless apocalypse into a slow galactic waltz whose steps can be calculated, modelled, and even visualized. The word destroy dissolves. In its place, tidal tails, starburst regions, and a merged Milky galaxy that will shine in wavelengths no human eyes will ever see directly. And yet, this moment, it's not small. Right now, on a single planet orbiting an ordinary star, a species that only recently learned what galaxies are is writing the first accurate chapter of that far future story. Equations on screens, photons caught by cold mirrors, spacecraft coasting far beyond the planets that launched them. This is how a civilization learns to look billions of years ahead and say with a straight face, here is what the night sky will become. Tonight, we're going to treat that as an invitation. If turning fear of the unknown into informed wonder feels like a mission worth continuing, then this channel, these deep dives, and your attention are part of the same long experiment. Because the next step is even bolder, taking all this new data and asking what else the old Andromeda story got wrong, and what almost no one predicts about our galaxy's future. So, when this video ends, do not rush to the next headline. Let the quiet of the sky sit with you for a moment. Andromeda is not racing toward us as a wrecking ball. The Milky Way is not waiting to be erased. The 2 galaxies are drifting through a long, patient, gravitational choreography that no human civilization will ever witness from beginning to end. Webb did not save us, it simply gave us a more honest version of a future we will never live to see. There is something almost gentle about that. The cosmos is vaster, slower, and stranger than the apocalypse headlines suggested. Stars almost never collide. Solar systems are reassigned, not destroyed. And the night sky that your distant descendants might look up at, if there are any descendants, if they are still on a planet, if any of those ifs hold, will be utterly transformed, but transformed slowly, beautifully, across timescales that dwarf every fear humanity has ever held. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.